Yeah, I showed you in the second lecture this formula and tried to show you some examples and said that, I mean, this is the simple formula, as I said to you. There, other people had a very similar formula, I mean, of the same spirit, with the same graphs appearing here, but other weights here, and also this exponential was completely different. Also, these things were completely different. And this is like the simpler version of it. And I want to recall the formula a bit again, because maybe not everybody understood everything at the first place. And so we had from the spectral curve sigma x, y, b. This generates our omega gn. And if we divide by this x1s up to dxn's, this was our w, g, and x1 up to xn, where if I write x1 or xi, I mean x of zi. And from the other spectral curve, if we exchange x and y, we had the checks. And also here the same notation. And this was the functional relation between these WGNs and WGN checks, where we have here WGN, x and y were a meromorphic function on the Riemann surface. These Bergman kernels were normalized at the A cycles. And what else is missing here? To understand this formula, so we have also this function S, which was e to the t over 2 minus e to the minus t over 2 over t as a formal expression. Then we have also this weights bar pi, the set I, h bar u I, which was this product over I in this set I, h bar u I s of h bar u I d over d y I w check n y I minus this delta of if I is equal to y1 minus y I1, let's say I2 squared. And these were generating all the series, the former series, and the h bars. Check 2g plus n minus 2gn. Check. Okay, good. So what is this? What was this sum over this graph? So I show you some examples. We had this bipartite graph with the round vertices and this bullet-filled vertices for n equal 3. So n was the number of these round vertices. They are labeled from 1 to n. What example I wanted to do? For instance, such kind of example exists. We have here 1, 2, 3. This would be with 2 loops. It would just contribute at genus G equal 2 or higher genus. And this set I was associated to this filled vertices where it encodes to which labeled white round vertices it is connected. So this set would be 1, 2, 3. This would be I prime, let's say 1 and 2. And this would be I prime prime 1, 1. So maybe another example would be this one, for instance, or so these are just examples which contributes a genus 2 or higher. So the difference between these examples is that we can have, so these bullet vertices can have any valence, but at least two. And we can have several of these edges connecting the same white vertices, the same labeled white circle vertices, etc., etc. Okay, good. Then we have also here the symmetry factor, which would be in this case, for instance, or let's write it just like this, would be in this case, because we can permute them 3 factorial. So I think from this example, one may understand roughly the structure of this formula, but still, we have here an expression which seems quite complicated, depending on these graphs. We have everything as a formal power series in h bar, and since h bar goes all the time with ui, we take here the ui to the mth coefficient of this whole expression, where here's a ui, here, etc. And then we take the mth derivative of this expression, and we sum here over all possibilities, and here over all graphs. So it's quite a long formula, but I say this is like the simple one. So good. So I've explained, I think, the formula again. Then we can look again at examples. So from topological recursion perspective, there are some quite interesting examples which are of the form that we have the Riemann sphere as the Riemann surface. X of z is some rational function. Y of z is just z, and the Bergman kernel is just z1, dz2, z1 minus z2 squared. So these examples include the example of the Airy curve or higher R spin intersection numbers if you want to compute, the Gaussian unitary ensemble from matrix models perspective for Hermitian one matrix model. Good. So this example implies that all W check n are 0 for 2g plus n minus 2 greater than 0, which means on the right-hand side where we have these weights there, for instance, this graph cannot appear because this object has 3 attached edges, so it has valence 3. This would be the case for g equals 0, n equals 3. It does not contribute. So for instance, in this example on the right-hand side, this will not contribute. This one as well, because here we have a 4-valent vertex, but this can contribute. Then what else? W check 0, 2 is of a very simple form. 1 over y, 1 minus y2 squared, which is the same as 1 over z1 minus z2 squared, because usually you have to divide here by the derivative of y, which is 1. So this is also quite easy. And this just contributes on this diagonal. So, and if we want to have something like this, where we have the diagonal, this term here would subtract this one, so also any graph where we have just this self loops would also not contribute. So we have a very nice subset of graphs which we can consider there, and the formula is probably nicer if you want. And we can do actually more. So graphs can have, for instance, this form where we have 2, I don't know, I and j from these round vertices. You can have several of these 2-valent bullet vertices. Let's say we have k of them, the automorphism would be k factorial. So just for this subgraph, and if we sum over all such kind of possibilities, we have this automorphism group to be 1 over k factorial. It's quite likely that you can sum this up to an exponential. So you have this prefactor 1 over k factorial, and you can actually sum everything up where you have something of this for each of these subsets of graphs, where you have something here, some new set of graphs probably, where you have 1 over the automorphism group of this some weights, that you can get like an exponential of this thing. So this is actually how the formula was first computed from this Fock space business by Sergey, etc. So they had like this in mind, but there was another more complicated function phi, which was included at that time. But this version I'm describing here was like the first version of this formula. And more precisely, we can pull this in an exponential. I maybe write it down, that we can define then a new weight depending on this object. So if we wrap everything in this exponential, which means that this object and we put everything in just one edge, but we have to expand this edge. So we have to expand this exponential. So this is like now an edge with a different weight. This weight depends then on this 2 circle vertices, and it would be of the form like exponential of the previous one we had before. So this is like, yeah, because I and j, now it's a different weight. J, h bar, ui, uj, minus 1, because we want to subtract like the leading order of the exponential. And this would be just of the form I, ui, uj in this one example, because we have here this simple form, zi minus zj squared minus h bar squared over 4 ui plus uj squared. So where does it come from? I said yesterday that we can also reformulate everything in the integral of this, in the primitive of this object. So if you integrate this with respect to z and then z squared, you get a logarithm, and then you take the exponential of the logarithm, which gives you something now which is of this nice form. So there are a lot of things which can be done. And in this form, the formula is, in my eyes, even nicer, because we have this nice example here, which includes, as I said, Airy curve and GUE. And I think I talked to Luca yesterday. He asked me about something he had in probability. I think this also includes what we talked about yesterday. So we have here y is the identity, but x is not the GUE example, but just another complicated rational function. Okay, so this is one thing one could do with this formula: rewrite it, wrap a few things together to an exponential. You can actually look here. This is the, you can think of, if you are from probability, this is the connected correlation function. We can look at the disconnected one. We sum over all set partitions, etc. Then you can actually wrap all these things together in the exponential. This is where it actually comes from. But we can also do a different way around. We can also refine it. And this is what I want to do now, show you a little bit the refined version of the left-hand side, but I will not talk too much, and I don't want to scare you too much. But we have also the possibility to make it, to make this h bar and u expansion. I mean, they are not independent, obviously, because each time you have a ui and the h bar, they come together. but you have an additional H bar expansion here in these objects. And they are all playing together, so the UIs, or all the sum over all the exponents of the UIs and the H bar are not independent, and that can also be done. So now what about the refined version? So what can we do? So we expand, for instance, a weight here. So one of these weights was associated to this bullet vertices. So we can have, for instance, let's assume we have this one as a subgraph. And if we expand an H bar, which means we decorate this vertex with a genus, Gi, let's say, here, coming from this H bar expansion, which is this Gi. But we have also an expansion of H bar coming from this S. So we have here also, like, just I write H1, H2, H3, H4. Expansions at these edges, which coming from the expansion of the S. And what are they doing? So this object would give us now the weight U, depending here is maybe I1, I2, I3, I4, maybe we write here H1, HI1, HI2, HI3, HI4. We would have the product over J from 1 to 4, Uij, H bar, no, the H bar, we took it out, Dyi j to the 2Hij, coming from the expansion of these S's, 2 to 2Hij, 2Hij plus 1 factorial. On this check Gi, we had, here we had like the 4 and the Y in this set I. So this would be like the refined version if we decorate all these edges and all these bullet vertices with which additional numbers. But what we did not consider yet was the exponential here. So the exponential is associated to one of these white vertices, and its H bar expansion would give us one valent bullet vertices, depending to which order you expand the exponential. So if you expand the exponential to the kth order, you have k of them. But each of them, again, has the same expansion as the weights. So we have here, again, like a Gi going down, and here some Hj, which gives you this decoration on one valent vertices. But we have here the important difference that we subtract something. And this subtraction gives us or restrict us that some, let's say for this example here, some Hj, let's write it this way, Gihj cannot be equal to 0, 0. So which is kind of stability condition, if you want, from, yeah, which we heard. So we can extend this definition of this graphs here by this additional decoration. And then we have maybe a nicer way to see where in this recursive formula, or where in this functional relation, each term appears. And the overall condition which holds is that the genus on the left-hand side is the sum over all the H over all edges, plus the sum over all the GIs of these bullet vertices plus the first Betti number of the graph. And if we do that, as I said, they're playing together, this H bar expansion and UI expansion, which gives us also some information on this degree of the derivative here. So this derivative dxi under this refinement mi goes to dxi ri of the graph gamma plus some 2 hi of the graph gamma minus 1. So this is like an Euler characteristic, as you can see. And the hi is the sum. We take some vertex, the sum over all the h's here around. So the sum, the hi is like the sum over all the h's at the circle vertex I. So there's a more refined version of it, and it can be written down in this way. And I think I don't know, from combinatorial perspective, I think it's a good idea to look at it and to I mean, if you want to prove something like that from combinatorial perspective at higher genus, I think this is the right thing you need to do, to look at more decorated graphs than we had here. Okay? But another thing, what I did recently is to look at the Laplace transformation of this formula. I mean, Laplace transformation is a very important thing in probability theory. We use it in quantum field theory. Actually, if you include your source term, this is essentially like a Laplace transformation, and then you take it at 0. So it's quite natural to do here. And the Laplace transformation plays a very important role in topological recursion. So it appeared like maybe where the idea comes from is already from Kontsevich, because Kontsevich, in his paper where he proved the Witten conjecture, needed the Laplace transform to go from the intersection numbers to the matrix model. And this was then done more complicated, let's say, by NR for any spectral curve. So whatever you have as a spectral curve, this has an interpretation on the modular space of complex curves. And this was done in complete generality. And he used the Laplace transform. So it's quite natural to look at the Laplace transform of this equation there. And what we will see, so first of all, I'll write down Laplace transform. And what we will see that these objects here will behave quite nicely under the Laplace transform. So actually these derivatives give us like products. So we get here products on this parameter we use for the Laplace transform. This thing here will give us a kind of variable transformation. And this part vanishes. So we take the Laplace transform on the left-hand side and also on the right-hand side, and a lot of very interesting things will happen. So which gives us a feeling why these terms are of this form. So let's do this Laplace transform just in one variable, not in n. It's like same. So on the left-hand side, so we will consider some paths which are on the Riemann surface. I don't want to be precise about them, so we make some assumption about them, but I think you can choose the steepest descent path, and it was done by NR, but I didn't look at all the general cases, and there is still some work to do and to understand this path of WGN x1 up to xn. So the ZI lives there, so we have here essentially ZI, and here also the Z1, etc., Zn. Times, good, almost forgotten, mu I x I, and then product over I. So this is on the left-hand side. We do the same on the right-hand side, and now I want just to write it down in one variable. So we have on the right-hand side the integral over this path gamma I, the xi, e to the minus mu I xi. And essentially, what is the form of this equation? You have some sum of mi, some high derivative with respect to xi, mi, ui, mi, eid, xi, times some function f depending on ji, let's say, and ui. So I wrap everything on the right-hand side, just in this function fi. So, and let's assume there is a path such that we can do partial integration. And all the boundary terms with respect to this partial integration vanish. What happens here? So we can integrate this part and take the derivative of this part. Gamma I dxi, so we have e to the minus mu I xi. And we do this for any mi here. So we have here a sum over mi. And instead of the derivative, we get just each time a factor minus mu I to the mi of ui mi. This factor still is there, and this as well. I, ui. Okay, this was the first step. But if we have here a formal expression in the ui's, and we take the mth coefficient and multiply by something with the mth coefficient, this is nothing else than just substitute everything with mu I. So e to the minus mu I xi. And then we can just write, also this sum completely disappears, so we can just write di dxi of f of yi and minus mu I. So we have form a series, we take the mth coefficient, we multiply by something of power m, so it's clear that this comes out. And now we integrate with respect to x of z, but we have here this factor, this derivative, playing all the time there around, and which explains us this. We have to look at differential forms as we do in topological recursion. But here at this point, it gives us like a variable transformation. So we can write this integral over the gamma I dy of zi of e to the minus mu I xi, where I will emphasize the zi dependence because this path did not change. And we have f of yi, which depends on zi minus mu I. So all this maybe not really natural structure in this functional relation where we take the mth coefficient and take the mth derivative, and we have also this shift here in the exponential, and also this term behaves very nicely under this Laplace transformation. So we have then that the Laplace transform of the WGN will be of this form. I don't know if I should write the whole equation down, but it's maybe very clear what happens. That this formal series we have here vanishes, the derivatives vanish, the UI vanish. This is like the variable transformation, this part. Oh, sorry. I should include it. So we have here also, if we have in this function f, there's one part coming from minus xi ui. Did not do that. So we have it also here minus xi ui. And then if we put ui to minus mu I, we have here e to mu I xi. This is what I forgot, sorry. And they cancel. So, yeah. It was also correct before, but now I just factored out this e to the xi ui. And this is even more, yeah, more beautiful, if you want. And okay, good. We have now looked at the Laplace transform of this object, and this functional relation behaves nicely under this Laplace transform, under the assumption on this path gamma, that all these boundary terms vanish. But what can we do with this? What can we do? So maybe I'm almost done. So maybe we look at examples. Again, we take now example of an example of an example, which hopefully shows you how general this formula is and how general it holds and what it can compute for you. Yeah. Yeah, that's completely right. But in the original formula. No. I mean, if you want to think about psi class intersection numbers, you need points. You need points. You have some marked points where you have your psi class. For instance, if you talk about psi.
So, if you say you switch you swap your spectral curve by change of roles of the x and y's.
Yeah.
Both codify some intersection numbers, but they will be of course different.
Yeah.
And so the question is, can one see directly which set of are exchanged, or it goes in this direction maybe?
Yeah, I will now do this example, where if we exchange x and y, all this w, g, and checks are 0. So this does not encode any intersection numbers. Everything is just 0. But this formula can be applied and gives us maybe a new way of computing, or a new algorithm. But it can, I mean, you're in principle right. It can give you maybe an interplay between different intersection numbers in your formula.
That was a question.
Yeah, this is a fair question, yeah, and I think it can do. I don't know how complicated it is. It's another question. So let's do the example which works here above, and then let's assume we do the Laplace transform of this example here above. So we look at the area curve. So which means x of z squared over 2 and y of z is equal to z. And then I mentioned it in my first talk that the omega gn's are k1 plus kn equal to 3g minus plus n minus 3. I guess so. Here we have the psi 1 up to k1 up to psi and kn gn. Then we have here this product 2ki plus 1. Double factorial equal to 2ki plus 2 dzi. Then what we can do? We can plug everything in. We can compute on the right hand side. We have this w checks for stable topologies is 0. The other one is not. We just take the sum of our So the sum over all graphs reduces to the sum over n-labeled vertices which are connected. So this is a very nice subset because we wrap all these multiple graphs coming there in this exponential. So a lot of cancellations appear. And another thing is that the Laplace transform of this object, here, so so 1 over 2 pi square root of n. Then here we have a power gamma dx to d1 dx dn of the e minus mu I x di, this wg n, where we insert this expression here, x1, etc., is nothing else than the intersection number of ELSB formula like structure. So we have here 1 minus mu I psi I gn. So this follows from this expression here. We just take the Laplace transform, where this part gamma goes from minus infinity plus some epsilon I and plus epsilon I plus infinity. And on the other hand, if we apply the Laplace transform of this formula and insert it, also wrap everything together in an exponential, etc., etc., this gives us the h bar to the 2g plus n minus 2 product over I from 1 to n e to the minus h bar 2 mu I over 3 over 24 h bar mu I 2 pi, which cancels. This one here coming from some integral, and then we have here an integral from minus infinity plus I epsilon plus infinity plus some I epsilon dzi e to the minus mu I zi squared over 2, which is just a Gaussian integral of the sum of these graphs g, let's say tilde n h bar squared mu I mu j, right, where I take here the product of all the sets I in this set I of gamma, where now this I consists of ij, just two elements, just a set of two elements, h bar mu I mu j over the I minus z2 squared minus h bar squared over 4 mu I plus mu j squared. The set of graphs is essentially where you have n vertices and you connect them just with one edge, at most one edge, so this is not allowed because we wrap everything in this exponential, but such kind of things are allowed. And and this is the formula. And I wrote this in my paper 2 weeks or 3 weeks ago, and then Sergey on the first day came to me. Yeah, do you know this paper? We have a very similar formula, and this is exactly of the same spirit. And this is like the easiest example. So where we have this Laplace transform, we have y is the identity, we have x is just the area curve. And if you want, you can specify even more the g and the n, and which gives us a very nice thing. So
how should one read this? This gives you another recursion, or this gives you relations fulfilled by the
What do you mean with recursion? I mean, this is a formula. You sum here over this graph.
If you the right-hand side is a number you calculate in terms of graphs, but the left-hand side gives you information of.
No, okay. So this is the formula. So this one here I use like as an intermediate step. So the formula is here you have the intersection number, it can be computed with this formula.
Yeah.
This is the formula, this is my statement. This was used as an intermediate step, so actually I wanted to write this is equal to this, and through this formula equal to this. This is how you should think of it. So I have 10 minutes, right? We have that's good. So, perfect. Even more time. And this whole business, as I said at the beginning, works for meromorphic x and y's, but this formula and also the Laplace transform works for the Lambert curve, which has a logarithm in it. So I computed this example, and we have a quite similar formula. I wrote it in my paper for the Hodge class integrals. So this would be then of the form. So here maybe first this product mu I to the mu I plus 1 over mu I factorial. Then you have here the sum over this Hodge classes mu I psi I gn. Where now the difference is we have one more term, one more factor of this S function appearing, and also these weights are different. I don't want to write down this formula, I just refer to my paper where it's written down. It's also of the same spirit, but we don't take here integrals from minus infinity to plus infinity. We don't have Gaussian integrals. We take rather residues, which is also a contour integral, right? And then we have here other things popping up. So essentially the zi's are not shifted by mu I, but multiplied by e to the, what is it, h bar mu I half. This, maybe one can do another transformation to make it similar, but more similar. But this is how it works. So we have the same graphs appearing, but we have here like a different weight we have to put on this vertex, and this Gaussian integrals are residues, and also this term is a little bit different because I mean this is very specific to the Airy curve. And I know that Sergey will told us more about free probability and maybe this connection to free probability, but I just want to show you the connection with my notation. Maybe he will use another notation and then it's maybe not directly clear, so I just want to explain how my notation is related to the generating series of higher order free cumulants, higher order orders in the moments, etc., etc. So maybe I should say that. So one of the very important steps to make this connection to free probability was, of course, the previous work of Sergey, Boris, and his collaborators, Elba, Guetton, Savarin, who show that these fully simple maps and ordinary maps are related by the XY symplectic transformation. This was a very important step before. And after that, you can use this functional relation. So they had in their paper where they talk about this analytic structure or analytic something about higher order free probability. The complicated version of this, and I simplified it to this form. And what is now the direct relation between it? The following. So they defined this MGN of x1 up to xn. I hope this will come up in Sergey's talk, but I don't know. Okay, and by Gn Kn, and here we have the product over I to n xi ki. So this is like the generating series of moments where they have a notion of explaining what this G is for. And there's also the generating series for the cumulants. The same, and here we have the kappa G semicolon K1 up to Kn. And here we have this product over Y, I, K, I. And okay, so it's maybe very natural to start from free probability perspective with these objects. But what I'm saying is that we actually have to use slightly shifted versions of it. Because for these shifted versions, this moment-cumulant relation is much simpler. So how are these mg n x1 up to xn are related to my w's is the following, that we write wgn 1 over x1, so this is a capital X, to 1 over capital Xn, minus, divided by x1 up to xn, delta n2, delta g0, this is maybe not really, x1, x2 here, x1 minus x2 squared, and there's the other one here, dgn is the w check gn y1 up to yn. So here we take the inverse, here not, but we multiply y1 up to yn. But we subtract also this m1, 0, also here y1, y2 divided by y1 minus y2. So this relation holds for these two objects, and they are related to the generating series of moments, higher order cumulants in this way. Just maybe to see, we had, so all this business in free probability started with Voiculescu and his R transform, which was of this form, in my notation C01 of x of M01 of x is equal to M01 of x. And now, using this definition here for G equals 0, N equals 1. So let's do it. So we insert, the C01 case. We have one check of x of M01 as before of x. But we have to multiply by y. Y is exactly our argument here. Which is M01. So this is cancelled. We can bring this to the other side. Then we insert here the definition. And we see, so we multiply by xi, and this is left, so we have here W01 of 1 over x is equal to 1 over x. So and this is what I said at the first talk, that these two functions are formally inverse to each other. And this is exactly here what we see from this R transform. And you can do the same for omega 0, 2, where you take your second order functional relation, and this breaks down to the one I showed you in my second talk, I think. Or my first, I don't know. Yeah, I'm actually think I'm finished. Yeah, thank you very much.